Welcome everyone. My name is Mario Mansalvas Paredes. I am a civil engineer with a master in civil engineering systems, and over the years I have developed a special bond for payments. For the next minutes, I would like you to join me so we can explore together my project called Smart and Sustainable Solutions for Road and Airport Payments, or simply SmartEcoPave. My project is part of a European trading network called SMARTI, which has been funded by the European Union Horizon 2020 program under the Marie Curie Actions. Within SMARTI, we are 15 researchers placed all over Europe with the sole aim of finding what will be the future of transport infrastructure. In my case, I landed in the UK where I joined the Nottingham Transportation Engineering Centre in 2017. SmartEcoPave has been carried out through a fruitful collaboration between the University of Nottingham and Michigan State University in the US, where I had a wonderful opportunity to work with some of the best professors in my field. For those who are not familiarized with pavement, you should know that traditional asphalt concrete is made of two components, aggregates and asphalt cement. However, selecting the type of aggregates and the asphalt cement is a complex task that will require its own explanatory video. Before moving forward, let me introduce the different parameters that affect the performance of a pavement structure. From a general viewpoint, we could say that those parameters are material selection and construction, loading type of weather condition, and finally, the maintenance and rehabilitation strategies. Material selection and construction are the ones having a high initial impact, therefore its importance. However, let us assume that we have a correct design and constructor, so we start building on pavement without problems. We will start loading the pavement repeatedly with different axle loads and wheel configuration over a range of temperatures which sometimes are extreme. Surface cracking will occur as a combined effect of material degradation, repetitive load application, and rapid temperature changes. Cracks can be classified according to its severity as low, medium, and high. Therefore, is there a way to monitor damage growth and to alert infrastructure managers so they can adjust their maintenance plan before it's too late? Actually, there are several options in the market, and some of them have been there for more than 30 years. This is the case for the well-known yet traditional and sometimes expensive strain gauge. Majority of these systems work through the application of an external load changing shape and size, thereby shifting its resistance. When sensors are embedded in the pavement layer, we expect to see a response histogram that changes with time and load application. Pavement engineers look for the compression-tension-compression cycle produced by the application of the load. Two definitions can be drawn from here: stress to be the internal resisting capacity of the system, and strain to be the amount of deformation. SmartEcoPave has focused on the piezoelectric sensors. This device uses the accumulation of electric charge in response to the applied mechanical stresses. Piezoelectric materials generate charge when squeezed, and that is exactly what we're measuring. Moreover, we have used a piezo film as our sensing device because it is flexible, lightweight, tough, and low cost. Our research has been divided into three main steps: laboratory comparison, full-scale validation, and sensor implementation. Laboratory was made at the Nottingham Transportation Engineering Centre through the use of 4-point bending machine and a national instrument data acquisition system. Our objective was to see if a relationship between the strain and voltage measurements could be found. To that end, we used a 10 mm dense bitumen macadam where temperature, frequency, and the induced microstrain level were varied. A total of 96 combinations were tested, allowing us to conclude that for the tested range, a positive and a strong linear relationship was found, and that frequency has a slight effect on the responses. The second step was the full-scale validation. For that, we used the fatigue carousel owned by the French Institute of Science and Technology for Transport Development and Network, also known as IPSTRA. The carousel is composed of 4 loading arms. Each arm can transmit a maximum load of 13 tons at a maximum velocity of 100 km per hour, allowing to simulate 20 years of traffic in months. Our sensors were located in one section of the carousel where no materials were used. This time, we wanted to see if piezoelectric sensors could be used outside the laboratory to monitor pavement deterioration. In order to do that, we deployed 4 strain gauges to be used as reference and 6 piezoelectric sensors along the test section. The experiment lasted for 4 months where 1,400,000 gloves were applied. Each arm used a dual with single axis configuration to transmit the load. Our experiment used 2 loads, 60 and 75 kilonewtons, and 2 loading speeds, 76 and 43 kilometers per hour. Results have shown us that piezoelectric sensors are able to measure changes in the pavement. It has also allowed us to determine an optimal sensor location which will be used in the future. And finally, we saw that all sensors had a higher survivability rate than the strain gauges. Overall, we found similar trends for both types of sensors along the entire test. This was extremely important to our research as it validated for the first time ever the use of this type of piezoelectric sensor for long-term pavement monitoring. Knowing how a pavement behaves under repetitive loads is important, but can we use piezoelectric sensors to find new ways of representing damage severity and growth? Well, we have found a way of combining the measurement histograms with various data analysis techniques to obtain cumulative sensor responses, which have allowed us to know when damage begins, how it grows, and when surface crack will occur, all very much needed for road authorities. Sensor implementation is the last part of the project and is where we currently are. We want to determine which is the minimum number of sensors to detect damage in a representative section of pavement or sample unit. Sample unit definition came from literature. Then we had to define the position of the wheel pads, location and number of the sensor, as well as the position of the weak nose, which is the combination of the asphalt modulus reduction and the extent of damage in the wheel pads. A random discrete uniform distribution has been used for modeling the allocation of sensor and weak node, whereas a random normal distribution has been used for modeling the wheel load position. For the artificial case generation, we have used 5 asphalt modulus reduction and 6 extents of damage. A total of 6,000 cases have been generated and are being analyzed. Below, you can see what a 50% asphalt reduction with 6% damage extent looks like after the wheel has passed. We aim to finish the data analysis in the next month. If you wish to have more information about my project, feel free to contact me through email or by the network of your preference. Thank you very much for watching. I hope you enjoyed the video.